Welcome to Section 4, Lesson 2. In the previous lesson, we set up the coordinate plane and learned how to plot ordered pairs in any of the four quadrants. Today, we add the two foundational measurements that connect plane geometry to algebra: distance between 2 points and midpoint of the segment connecting 2 points. The distance formula comes directly from the Pythagorean theorem applied to the right triangle formed by the horizontal and vertical separations between the 2 points, while the midpoint formula is just the average of the coordinates of the two endpoints. Both formulas are short enough to memorize in 5 minutes and are in continuous use across the rest of Section 4, all of Section 15 on conic sections, and into calculus, computer graphics, and physics. Today we lock in both formulas with one clean example each. First idea on the board. The distance between 2 points x1, y1 and x2, y2 on the coordinate plane is computed by the distance formula, the square root of the quantity x2 minus x1 squared plus y2 minus y1 squared. The formula comes from the Pythagorean theorem applied to the right triangle whose legs are the horizontal separation x2 minus x1 and the vertical separation y2 minus y1, with the hypotenuse being the straight line distance between the 2 points. Second idea, the midpoint of the segment connecting 2 points x1, y1 and x2, y2 is the point whose coordinates are the averages of the two endpoints' coordinates x1 plus x2 over 2 and y1 plus y2 over 2. The midpoint formula is just two arithmetic averages, one for the x-coordinate and one for the y-coordinate. The formula is structurally simpler than the distance formula because no squares or square roots are involved, and it has the natural interpretation that the midpoint sits exactly halfway between the two endpoints in both dimensions independently. Both formulas are foundational and recur in every later analytic geometry lesson. The distance formula appears in the equation of a circle in the slope-distance relationship for parallel and perpendicular lines, in the optimization problems of calculus, and in collision detection algorithms in computer graphics. The midpoint formula appears in the perpendicular bisector construction, in the centroid calculation for triangles, in the average position calculations of statistics, and in many physics formulas for center of mass and equilibrium. Memorize both formulas now, and they will pay off across hundreds of later problems and applications. Today's two examples walk through one clean distance computation and one clean midpoint computation. The distance formula comes from the Pythagorean theorem. Given 2 points x1, y1 and x2, y2 on the coordinate plane, the horizontal separation is the difference x2 minus x1 and the vertical separation is the difference y2 minus y1. These two separations are the legs of a right triangle whose hypotenuse is the straight line distance between the 2 points. The Pythagorean theorem says the square of the hypotenuse equals the sum of the squares of the legs, so the distance is the square root of the sum of the squared differences. Here is the distance formula in symbols. D equals the square root of the quantity x2 minus x squared plus y2 minus y1 squared. Memorize this one line. It is the same Pythagorean theorem you have known since middle school, just written in coordinate form. The formula works regardless of which point you label as 1 and which as 2, because the square differences are unaffected by sign. Here is the midpoint formula. The midpoint of the segment connecting x1, y1 and x2, y2 is the point whose coordinates are the averages of the corresponding endpoint coordinates. M equals the ordered pair x1 plus x2 over 2, y1 plus y2 over 2. Two simple averages, one per coordinate. The midpoint sits exactly halfway between the two endpoints in both the horizontal and vertical directions independently. Step 1 in the workflow for distance. Identify the 2 points and label one as point 1 and the other as point 2. Subtract the x coordinates to get the horizontal separation and the y coordinates to get the vertical separation. Square each separation Sum the squares, take the square root, and the result is the distance between the 2 points. Step 1 for midpoint. Identify the 2 points the same way. Add the x-coordinates and divide by 2 to get the midpoint x-coordinate. Add the y-coordinates and divide by 2 to get the midpoint y-coordinate. Combine into the midpoint ordered pair. Both formulas are mechanical once the 2 points are correctly labeled, and the verification step in both cases is a quick sanity check on a sketch of the figure to confirm the numerical answer makes geometric sense. Here is the first worked example. Compute the distance between the 2 points 1, 2 and 4, 6. Apply the distance formula directly using the Pythagorean theorem framework. Step 1. Label the points. Let 1, 2 be point 1 with coordinates x1 equals 1 and y1 equals 2. Let 4, 6 be point 2 with coordinates x2 equals 4 and y2 equals 6. The labels are arbitrary. The distance formula gives the same answer either way because the differences are squared. Step 2. Compute the horizontal and vertical separations. The horizontal separation is x2 minus x1, which equals 4 minus 1, which equals 3. The vertical separation is y2 minus y1, which equals 6 minus 2, which equals 4. The two separations are the legs of the right triangle. Step 3. Apply the distance formula. Distance equals the square root of 3 squared plus 4 squared, which equals the square root of 9 plus 16, which equals the square root of 25, which equals 5. The distance between the 2 points is exactly 5 units. Step 4. Verify by sketching the right triangle. The 2 points form a triangle with horizontal leg 3, vertical leg 4, and hypotenuse 5. This is the classic 3, 4, 5 right triangle, the simplest Pythagorean triple, and the result of 5 for the distance is consistent with that geometric pattern. Sanity check passed. So the distance is 5 units. The big lesson from this example is the mechanical application of the distance formula. Label the 2 points, compute the 2 coordinate differences, square them, sum, take the square root. The result is the straight line distance between the 2 points in the coordinate plane. The example produced a clean integer answer because the inputs were chosen to form a 3, 4, 5 Pythagorean triple, which is unusual. Most real distance computations produce irrational square roots that you simplify or leave in radical form. The procedure itself is the same regardless of whether the answer is clean or messy, and the procedure is foundational to every later analytic geometry topic in the course. Here is the second worked example. Compute the midpoint of the segment connecting the 2 points -3, 7 and 5, -3. Apply the midpoint formula directly using 2 coordinate y's averages. Step 1. Label the points the same way as before. Let -3, 7 be point 1 with x1 equals -3 and y1 equals 7. Let 5, -3 be point 2 with x2 equals 5 and y2 equals -3. The labels are again arbitrary because addition is commutative. Step 2. Compute the midpoint x-coordinate. Average the two x-coordinates x1 plus x2 over 2 equals -3 plus 5 over 2 equals 2 over 2 equals 1. The midpoint x-coordinate is 1. Step 3. Compute the midpoint coordinate. Average the two y-coordinates y1 plus y2 over 2 equals 7 plus -3 over 2 equals 4 over 2 equals 2. The midpoint y-coordinate is 2. Step 4. Combine into the midpoint ordered pair. The midpoint is the point 1, 2, exactly halfway between the two endpoints in both the horizontal and the vertical directions. Verify by checking that the midpoint sits between the two endpoints geometrically. X equals 1 is between -3 and 5, and y equals 2 is between -3 and 7, so the midpoint sits inside the bounding rectangle of the two endpoints, which is a quick sanity check. So the midpoint is 1, 2. The big lesson from this example is the mechanical application of the midpoint formula. Label the 2 points, average the x-coordinates, average the y-coordinates, combine into the midpoint pair. The procedure is structurally simpler than the distance formula because no squares or square roots are involved. The handling of negative coordinates in the averaging is also worth noting. -3 plus 5 equals +2, which is fine because the average is allowed to land in any quadrant depending on the endpoints. The midpoint formula always produces a single specific point that sits exactly halfway between the two endpoints in both dimensions independently. Combining the distance and midpoint formulas, you can describe almost any line segment on the coordinate plane completely with these two short formulas alone. 3 mistakes that catch every algebra student during their first weeks of distance and midpoint work. Each one is fixable with a small explicit habit applied on every problem. First mistake: inconsistent subtraction order or sign error in the squared differences. The distance formula is symmetric in the 2 points because the differences are squared, so x2 minus x1 squared equals x1 minus x2 squared either way. But students sometimes write the differences in inconsistent orders across the two coordinates and lose track of which sign goes where. The fix is to commit to a consistent order at the top of the problems. Always do 0.2 minus 0.1, both for x and for y. Consistency removes the sign ambiguity and matches the textbook formula exactly. Second mistake: forgetting the square root at the end of the distance formula computation. A student computes the squared horizontal separation as 9, the squared vertical separation as 16, sums to 25, and writes 25 as the distance. The correct distance is the square root of 25, which equals 5, not 25. The square root step is essential and easy to forget when you are excited about getting a clean numerical sum. The fix is to write the square root symbol explicitly in every step of the formula and never drop it. Third mistake: sign error in the midpoint average when the two endpoint coordinates have different signs. A student averaging -3 and +5 writes -3 plus 5 over 2 and gets -4 over 2 equals -2 when the correct sum is +2 and the correct midpoint coordinate is +1. The fix is to compute the sum as a separate explicit step before dividing, so the sign of the sum is clearly visible. -3 plus 5 equals +2, then divide by 2 to get +1. Doing the sum explicitly removes the sign error. The distance and midpoint formulas are the workhorse measurements of all of two-dimensional geometry and underpin a huge variety of professional applications across science, engineering, and computing. 4 broad sectors below. In GPS and navigation systems, the straight line distance between two locations on a map is computed by a generalization of the distance formula that accounts for Earth's curvature, but the underlying logic is essentially the same as the planar distance formula you learned today. Mapping software, route planning systems, and emergency response dispatch all rely on this kind of distance computation continuously, with millions of distance calculations per second across the global navigation network. In computer graphics and game engines, collision detection between two sprites or two three-dimensional objects often reduces to computing the distance between their center points and comparing to a sum of radii threshold. The distance formula you learned today is the two-dimensional version of this calculation, and the three-dimensional version adds one more squared difference term inside the square root. Every modern video game and 3D simulation runs the distance formula constantly during gameplay. In physics, the center of mass of two equal mass particles sits at the midpoint of their positions, computed using exactly the midpoint formula from today. For unequal masses, the center of mass shifts toward the heavier particle, but is still computed as a weighted average of positions. The center of mass concept is foundational to mechanics, structural engineering, robotics, and many other fields. In statistics and data analysis, the Euclidean distance between two data points in any number of dimensions is computed by the multidimensional generalization of the distance formula. Cluster analysis, nearest neighbor classification, and similarity scoring all use distance metrics extensively. The mean of two equal weight observations is also the midpoint of their values, an averaging operation that appears everywhere in statistical work. The skills you build today scale across all of modern computing and quantitative work. 3 things to take with you from this lesson today. The distance and midpoint formulas are the foundational measurements of analytic geometry and underpin everything from GPS to physics simulations to data analytics across the modern technical world. First, the distance formula computes the straight line distance between 2 points x1, y1 and x2, y2 as the square root of the sum of the squared differences in the coordinates. D equals square root of x2 minus x1 squared plus y2 minus y1 squared. The formula comes directly from the Pythagorean theorem applied to the right triangle whose legs are the horizontal and vertical separations between the 2 points. Memorize this one line and use it on every distance problem in the rest of the course. Second, the midpoint formula computes the point exactly halfway between two endpoints by averaging their coordinates. M equals the pair with x equal to x1 plus x2 over 2 and y equal to y1 plus y2 over 2. Two simple averages, one per coordinate. The midpoint sits exactly halfway between the endpoints in both the horizontal and vertical directions independently. The formula is structurally simpler than the distance formula and has many uses in the rest of the course. Third, the two most common errors are forgetting the square root at the end of the distance formula computation and making a sign error in the midpoint average when the endpoint coordinates have different signs. The fixes are to write the square root symbol explicitly in every step of the distance formula and to compute the sum as a separate step before dividing in the midpoint formula. Both fixes take less than 5 seconds per problem and prevent the most common mechanical errors. Coming up next, the lesson called slope, where the steepness of a line is captured by a single number computed from the rise over the run between any 2 points on the line. Slope combines the distance formula kind of coordinate difference thinking with the equation solving machinery of section 3 to give the foundational concept that the rest of the section builds on.